Good evening, everyone. My name is Mark Berry. I think I've met or know all of you already, but I'm the president of Schoodic Institute, and it's my honor tonight to welcome our speaker. But I also want to thank all of you for being here, because you're obviously the hardy souls that were willing to be out on the roads in the snow today. And when we planned a winter festival, we didn't know what we'd get, but we sure got some winter this year. And we're enjoying it. Do be careful if you're on the road tonight on your way home. We do have the morning's activities and the early afternoon activities are on tap and continuing as planned tomorrow, but we have postponed the ice cream social, which I'll admit I'm pretty disappointed about because Pugnuts makes some pretty good ice cream. So you'll have to watch our newsletters and things for the rescheduling of the ice cream social and the rescheduling of the film that we were going to show tomorrow night, The Great Alone. So it's a film about the Iditarod and a particular sled dog, and it's an award-winning film. And by odd circumstance, one of the pups of that dog is in the community over on MDI, and its trainer and its owner were planning to be here tomorrow night. So hopefully that will be possible when we reschedule as well. But you all know Schoodic Institute to some extent already. We're dedicated to advancing ecosystem science and learning for all ages. We're a nonprofit that partners very closely with Acadia National Park. I'm going to keep that part of the introduction really short tonight because we're among friends. And that story isn't entirely new to any of you, but if you have questions, please reach out to me at any time about what the Institute does, why, how, who we work with. I want to focus on getting to our speaker as soon as possible. I think his reputation has probably preceded him to all of you. Dr. Hal Borns, somewhat of a legend here in Maine and beyond. He is the founder of the Climate Change Institute at the University of Maine, a 50-year career at the university, 28 field seasons in Antarctica, geological field work on every continent except Antarctica. He's almost certainly the only person in the room with a glacier named after him. And tonight, we're really looking forward to hearing about the Ice Age Trail and some of the remarkable evidence of glaciation here in our home state and almost in our neighborhood. So with that, thank you so much for being here.
Wait a minute, I'm gonna turn this thing on. How's that? You'll have to sounds loud to me. I think you can control it if, not sure. Well, I have to apologize. I have an allergy that's kicked in, nothing contagious. I have to drink some water and chew a lozenge. I'm recovering from a new hip, so that's what this is all about. So at my age, I guess I'm okay, but anyways, that's what it is. We're going to talk a little bit about the Ice Age Trail as that map is there, but it gives you an idea. But for many years, when I came to the university in 1955, very little glacial geology, and I'm a glacial geologist, very little glacial geology had been done since the 1930s. And in 1950, radiocarbon dating became a reality, and so things automatically changed because we could put dates on events at least back to about 60,000 years with a radiocarbon method. So I started in mapping geology with the help of the National Science Foundation mostly. And I started on the Kennebec Valley because I thought that as the ice went back in Maine, you get a very good record in the valley because the meltwater had to drain from the ice down those big north-south valleys. But the Kennebec was unique in the sense that as the water came down off what's known as the high area called Moosehead Plateau, it cut down so you could see the stratigraphy in the valley layers, and those layers reflect what's going on with the meltwater and hence with the ice. And so that's where I started. And then starting down east, a number of years ago, I came this way after reading about some of the geology. I had no idea what they were talking about from the 1920s. They talked about these big gravel plains as wash plains, W-A-S-H. I'm a Bostonian, so it comes out differently, wash. And so having taken a few trips through that, I realized there was an enormously good record here in eastern Maine. And so I started in, and between working here in Antarctica and other parts of the world, because I belonged to the state university, I had a dedication, a sense that I really wanted to work in Maine as much as I could. So we started in with graduate students and others, and we mapped the area from roughly the glacial deposits from roughly Acadia down to Lubec, and then across the border into New Brunswick. And out of that, and that was all published. And one day I was talking to a woman named Pamela Person, some of you perhaps know, and she said, Hal, you got all that great geology and it's published in scientific journals. Why don't you give it back to the public? How do you do that? Well, you make a trail that goes through it like Washington State, Wisconsin did. They have an Ice Age trail. Their geology is different, but their concept is the same. So I said, great, we got the work all done. All we got to do is make a map. 5 years later, the map got published because I had to go out and raise the money to hire a person who was a designer. I couldn't do it. I could make a map all right, but that's the result of a very, very good cartographer type person. And he also was responsible for all the plates in the newly published last year as the Historical Atlas of Maine. Big thing with many, many plates showing different layers of history. So I hired him, and that's where the money went, and the map got published, and out it came, and we distributed 10,000 copies to public areas and anybody that wanted them, and then after that, we redid another 10,000, and this is one of them, and we're at the end of this, but we charge for this one. There's no money that comes into my pocket or anybody else's, but we collect the money, and when this runs out, we'll have the money to redo another form of it. So that's it, but that's the whole history of this thing. Now that what I'd like to do is talk about the Ice Age, and in fact, what we're studying here is the footprint of a glacier. And the only way you can study ancient glaciation is to look at what the glacier did and then interpret it in terms of the history of glaciation. So what I thought I'd do is go through this a little bit quickly and then bear in on the deposits in that area a little bit more and just show you examples of the footprint. All right? So that's what we're going to do. I don't think I need this cane anymore. If I fall down, someone please pick me up. That's good enough. Now, can we put the lights down a bit? I'm sure that's fine. I'm sure you recognize this. This is obviously a snowflake. If we don't have snowflakes, we don't have ice and we don't have glaciers. And so the glacier is a collection of snowflakes that accumulate over time. In the Antarctic, the ice sheet is 3,000 feet thick, 3 miles thick, and that represents accumulation of snow at a rate of about 1/4 of an inch a year over a long period of time. It started to form 5 million years ago. So we had an ice sheet like that, but the beginning of it is this, the big snowflake. Earlier on in the 1600s, 1700s, right up into the 1800s in parts of the world, there was no such thing as continental glaciation. People knew there was ice in Greenland. They knew a little bit about the Antarctic, not very much, however, until after the beginning of the International Geophysical Year in 1958 and 59. But so what about all these boulders sitting on the landscape? Where did they come from? In Norway, they decided that these boulders were put in place by trolls. And trolls can come in all sizes, small trolls and big trolls that can throw rocks around. The little people in Ireland can't throw boulders because they're always little. But the Norwegians have got a different approach to this. And so here's a boulder from this area, and that's been put in place not by the wife of my colleague, but by trolls. And here's this lower picture is from the same area, and here's, you can see this ridge going along. It looks like a wall. That's what it is, and this is called the Trolls Wall. You say, well, why did the trolls build a wall? No one knows, but that's what they did, and there's the wall. But if you look at that closely, you see there's a lot of brownish vegetation on this side and none on this side. This is because the ice advanced, ripped up all the vegetation, and this was the edge of that ice mass, and boulders were transported and dropped off the edge. You know, this was about 1730 in this case. So there we have the troll theory, and there are other theories, and I'm sorry, I realized I got this in backwards, but it doesn't matter much. This is the first state geologist of Maine, Charles Jackson. And he, in 1837, published the first geological map and text on Maine. He was hired by the legislature to do this. And so he did, and he attributed all the glacial stuff to the biblical flood, Noah's flood. No mention of ice at all, and this is 1837. This man is quite famous. He he did a lot of different things. He was a medical doctor. Medical doctors prior to antibiotics and anesthesia couldn't do much, and they had a lot of time. They became naturalists, most of them, a lot of them, and he was a naturalist, but he ran a company in Boston. And he's given the credit for inventing, first person to invent anesthesia, which allowed doctors to go make cuts and do things inside of us. And that was that man right there. We can thank him for that invention. That's 1837. Here's another man in 1837. It's very different. This is Louis Agassiz. He was probably one of the outstanding naturalists of Europe, and he roamed the Alps and talked to natives and realized that a lot of the glaciers in the Alps that you could stand in front of had been much greater in extent. In other words, he'd stand at the edge of the ice and he'd look at the scratches on the ledge and the boulders, and then he'd move down 1,000 feet, and there's the same thing, and pretty soon he's down 3 miles, and the ice is back there, and so he concluded that we had been glaciated, and he, being a very well-known person, had the ear of the scientific population, and in 1837, same year as our man was working here, he announced a holistic view and said the Earth had experienced an ice age. And holistic in the sense that if you build ice, the water's got to come from the ocean, therefore oceans go down, the ice is built, got to refrigerate the Earth, animals have to migrate to stay ahead of the ice coming down over the continents. Some of them can't make it, like earthworms. When the ice left Maine, there were no earthworms at all, or anywhere else in North America, north of the glacial margin. They've all come back, but some animals became extinct, some evolved, and so forth. So that was all part of the holistic view of ice. And he did this in the middle of the time when the clerics of the world were arguing, you're crazy, this was the biblical flood. And he said, no, it wasn't. And here's why. And he proceeded to tell it. But continued up through in Maine until this man came along, another medical doctor from the Rockland, Camden area, and he started making very critical observations and published put together a 5-inch handwritten book in 1869, and the title of it is Footprints of the Last Ancient Glacier of North America. He realized that we're looking at glaciation, we're not looking at anything dealing with a flood. And for example, he made critical observations. The earlier people decided that the flood was a cold ocean over Maine, for reasons I don't know. Well, I know why, because there were fossils collected out of gravel pits, and there were Arctic forms. And to make the scratches on ledge, they visualized icebergs with rocks in the bottom, which they could see today in the Arctic, and they drifted along, hit the ledge, scratched the ledge, but he pointed out that how do you get an iceberg to go scratch legs upslope and then downslope? You can't make an iceberg float high and then low. You can't do it. Icebergs will go around hills, but they won't go up and over. He said, you've got to make critical observations, and you'll quickly realize that these were not icebergs, they were something else. So anyways, he's a very famous person. I came to own that manuscript accidentally. I won't go into it. It was deposited in the Portland Society of Natural History a long time ago, and when that society was physically destroyed by the Audubon Society in Maine, a real tragedy, the stuff went to the winds, and I ended up with this manuscript, and I thought, what is this? And that started the search, and last year, 2 of us translated that into printed form, and Springer has published the whole manuscript for us. So it finally got, and it is a revolution in scientific thinking in the 19th century, right here in Maine. So that's John Delaski. Well, so much for that. So here we are today with what we sort of understand, and this is not the map I wanted. I couldn't find the one I wanted, but this is the last ice sheet to cover North America. And one of the signs of what an ice age is that the Earth refrigerated to the point where ice could form at mid-latitudes, north 45 degrees, both here and in Europe. And when that happened the last time, it was 2.5 million years ago when this was achieved, and we've gone through several iterations of ice sheets. But this is the last one. And this covered North America, centered around Hudson Bay, and here's Maine here under ice, completely under ice, the Bay of Fundy, Long Island, New York, and you can see. And then secondarily, there's another ice sheet. I've lost my pointer here. Where? Button. This is all formed over the Rocky Mountains. Here's the big one and then the little one, and they merged in the middle. You notice in this picture, this is my drawing, we put in vegetation. All this, for example, is tundra with no trees at all, then tundra with few trees, and then mixed hardwoods down here. It's also where sea level was at the time is around. Hey, one of the signs of old age is how close can you hold a button steady? If I hold it with both hands, it's better. Try that as an experiment. But anyways, that's the ice sheet we're talking about. That's our ice sheet. And here's the same thing at the same time in Europe, over Scandinavia, and the Alps are separate. And here's Dublin, for example. That's London. So the ice came down to roughly London and across to Dublin, and then out here into the North Atlantic, and there's Greenland, and Iceland, and the climate zones, as Agassiz predicted they'd be compressed. Now, let's talk about footprint. This is the edge of the Greenland ice sheet about 15 years ago, up in a place called Kangerlussuaq, Stromfjord. Some of you have been there. There's a big Air Force base. But this is the edge of the ice sheet, covers all of Greenland. And you notice out here, there's a line. That's where the ice sheet was not too long ago, in the middle of 1700s. And beyond that, it didn't exist. So it was out here, and it left all sorts of deposits in here, and that is the footprint of the ice sheet. Now, let's look at the footprint of our ice sheet. This is Long Island, New York, and the ice came south over all of New England. And let me start by saying the ice started to flow. It had backed up a ways in a slightly earlier pulsation. It had not backed up, melted back to the Hudson Valley and the St. Lawrence lowland. Started to advance up around Quebec City, and it flowed from Quebec City southeastward across all of New England, across Maine, across the Gulf of Maine, and terminated on the continental shelf. That ice sheet started to move at about 25,000 years ago. The termination on the outer shelf was at about 20,000. And at 20,000 years ago, this is the edge of the ice out here, and there's George's Bank, and here that you're familiar with, we fish out there. And out here, the ice flowing met the ocean. It didn't meet the ocean over here. This is when the ice was building Long Island, New York, Martha's Vineyard, Nantucket, and out here, the shoreline was out here, so you could walk from Long Island, New York, out 40, 50 miles before you came to the ocean's edge. And this is because sea level was lower. Of course, there's another side of this, is that the land level was lower also, because the weight of land pushes the land down. So we got a kind of a complex situation, because as sea level came up, the ice disappeared, sea level came up, land level came up to where they are today. So, but that's the general picture. I've told, these are lines constructed from red rocks, for example. Red rocks from the Bay of Fundy come down this way, and you find a lot of them out here. This is the work of Woods Hole Oceanographic Institute. And these represent different rock types that have been traced quite easily out through here. And Long Island, New York is a big ridge of debris scraped off this part of New England. So Long Island, New York is the dump of New England. On the other hand, given perspective, it's the cream of the crop. It's the cream of England. New England has been scraped off and left in New York. But anyways, that's the edge of the ice, and this was achieved at about 20,000 years ago. If you trace this margin westward, and I don't have anything, it goes around through the Great Lakes, and finally comes out in Montana and areas like this, and this is the edge of the ice out there, and you can see a distinct footprint. This was where the ice came. It left all these boulders, these are the size of houses, along through here. This was all sand and gravel washed out, and it's become the big wheat belt of the United States. So this is the edge of the last ice sheet. This is 20,000 years old. It's the same as Long Island, New York. And everything north of that line is glaciated. Nothing to do with the Great Flood. As Agassiz said, the climate zones changed, and as the earth refrigerated, it got very cold up here. The cold here moved south. The wet zone up in here moved south into the desert zone, and that was a very moist area at 20,000 years ago. And big lakes like Salt Lake and all these big lakes formed. Then when the climate changed, the ice melted back, we went back to a desert condition in that part of the Southwest. So it's all tied together just like Agassiz thought it was. This is a very poor slide, but it gives you the idea. This is Woods Hole again. And what they were doing is I want to show you that we do have measurements on sea level collapse. So as the ice reached its maximum, sea level around the world was lowered. And so at 35,000 years ago, sea level, using the central line, sea level was there about where it is today. About in here, around 15,000, it was about as low around the world, as you can imagine, and then as the ice melted, it came back up to the present. This figure really is down closer to about here, and we know that sea level around the world was 300 to 400 feet lower than it is today. 300 or 400 feet lower, globally, all right? So what's that do? It lowers it below the Straits of Gibraltar, and so the Mediterranean became a lake. Mediterranean Ocean dried up, became farmland. The ice melted, sea level came back up, flooded into the Mediterranean for 1,000 years across the Straits of Gibraltar, filled up that, moved up into up the Bosphorus, into the Black Sea, and flooded Black Sea, and all the people put stuff on rafts and ran. That's Noah's flood. That's where it comes from. The story comes from the Sumerian culture. It's 2,000 years before the American, or the Bible, Christian Bible was ever written. But there is a flood, and that's where the flood was. You read the tale of Gilgamesh, and you read about this. But the point is, there's a record. We have a much better record now of that. Glaciers, when they move along, have rocks embedded in the bottom, mostly. And those rocks rub on landscape, on the ledge, and they gouge the landscape. And so here's a case of this, easily. This is water. Here, it's right along the shore down this way. In fact, it's down around Eastport. And the ice moved from here, and there was a rock stuck in the ice that made this long groove. All over. And then you can tell, but when you have a scratch, which way did the ice move, left or right, up or down? It moved from here because if it had come from seaward, this is ocean water right here, if it had come this way, this surface would be all smooth and striated, and the scratch would go this way, but it didn't. It went this way. The ice being somewhat rigid at the bottom didn't conform to that slope, it just bridged it, and so it goes. Anyways, that's one of the things. This is something you should be familiar with. This is not a new picture, but this is the Woodland Studio in Ellsworth Falls. And this rock right here has got these scratches on it, like this. This was reported by Louis Agassiz, and it is the first evidence, published evidence of glaciation in North America. First evidence, published evidence in North America. And so David Smith and myself, David is a historian that died a number of years ago, he and I managed to submit this to the National Register of Historic Places, and that's where it is today. So you can see that on the way south, the railroad tracks are right over here. That's the Woodland Studio, and this man is very proud of this, so he's taken all this up and planted flowers and kept the stuff off of it. It's a very famous historic place for North America. And they've just redid the road around it. The highway department, of course, recognized this and didn't touch it. This is Astrid Anderson. This is my colleague's friend on the side of Oslo Fjord a number of years ago. And you notice the scratches here. But you notice the shape of this thing. As the ice goes this way, there's nothing, these are cracks in the rock like this. And so the dragging of ice across this has a frictional drag to it. And when it comes to a situation like this, tends to drag this block away, this way, because of the crack system, and you perpetuate a cliff like this on the down ice side of these things. And they're given the name Roche-Moutonnet. It's a long story, but there's a lot of them, and almost every hill in Maine is this shape, bedrock hill. And they can be little or big or whatever. For example, this is a familiar site, the rocks, the islands off Acadia. These are also Roche-Moutonnets. The ice came this way, steep drop off. Same thing here. Same thing is true over here in the Tunk Lake Hills, and so forth. Here's another example. This is shales, mudstone and sandstone. It's about 400 million years old, just outside of the town of Bar Harbor. And here's a granite boulder that doesn't belong there. And the Indians didn't bring it, as some people say. The trolls didn't throw it, but it did come from Dedham, about 10 miles to the north. So here we have a way of measuring glacial transportation and direction with these things called erratics. Base of a small glacier in the Antarctic. Notice the water. Gets up to freezing sometimes in the summertime. And remember, the summertime is now in the Antarctic. Just barely now. It's getting close to a fall. But this is debris at the base of the glacier. Our glaciers around here didn't have these vertical faces. These are polar glaciers, and it has to do with lack of meltwater. But you can see the debris at the bottom. That's the point. This man is George Denton. He's on the staff at Orono. He's the only person in the state of Maine ever to be elected to the National Academy of Sciences in the United States. The only person from this state that's ever been invested. We have people here, but they got that honor somewhere else. This man did it at the University of Maine, and so forth, for good reason. He was an undergraduate here. This was 1960, I think. If you look, that last picture shows the debris. This is what it looks like when there's no ice. This is what you see plastered all over Maine, because as the ice sheet moved, it scrapes this stuff off the bottom like you scrape mud off your shoe, and it's a mixture of sand and gravel and a lot of clay and a lot of big boulders and little boulders, and it's completely a hodgepodge of material because there's no way you can sort things into big things and little things at the base of a glacier. You can't make layers of sand, layers of pebbles. So that's what this stuff looks like, and I suspect when I took this picture in the northern part of Maine, I'd also point out that one of the characteristics of this kind of deposit are the boulders that are transported, and the transported boulders are squared off because they're scraped along and they wear flat. There's another one up here. A lot of them are angular, they're flat, and they're very often scratched. And this is till, T-I-L-L. And that's my trenching tool, and to my knowledge, it's still sitting there on that outcrop up in the North Maine woods. I went away and left it. And I don't know where I left it exactly. An old picture that was done for a reason several years ago, forgetting that date, but the ice was out here. This is dry land. The ice came along here, went out here, crossed over and went out here. And so it's in this area, the ice was in contact with the rising ocean, and the ice receded in contact with the ocean. So the deposits along the eastern coast of Maine are glacial-marine deposits. They're ocean, where the ocean fronted against the sea. Again, this isn't a very good map, but it gives you the idea of what we're talking about here. This is an early map I made for some reason, and here we are in Cherryfield, and that is the naval station down at Cutler, and then Eastport, and so forth. And so here we are. Stu Bend is here, and these are deposits, ridges formed at the margin of the ice in the ocean, and the ice margin was receding like this. Here it's like this. It was receding here, and so forth. And and this is one of the big areas of the blueberries up behind Cherryfield. All built the same way. This is how they were built in the ocean. Took me about a year before I could figure this all out. People had never seen these kinds of ridges. These are called moraines. And most of the moraines of the world are made of till. They're pushed up by the ice. But here we're dealing with an ocean, and these moraines are full of sand and gravel. So I spent some time in Norway looking at marine end moraines, and came back here and looked at them again. That's what we've got. These are called grounding line moraines. This is the point where the ice is in the salt water, and it's just going afloat here. and kicking out icebergs. And we've been reading about an ice shelf in the Antarctic that's breaking off now. That means that this glacier was spread out like this as a floating shelf, and it's breaking off today. Breaking off a piece the size of Delaware at the present time. But the ice moves along, transports rocks and sand and gravel. They come up here and get dumped out. This is tilly stuff, this is sand and gravel, and this is ocean bottom clay. Because in this grinding mill at the base, a lot of rock gets ground up into flour. And we look at it today in Maine, and it's called the blue clay. And it gets into the water, and water's all gray, and it settles out like this. That's how these ridges are formed. And here's one that you can look at. This is Cherryfield is right up here, and the road, I can't see it, but the road between Ellsworth or down east of Ellsworth, 182 or something, comes across like this to Ellsworth. But this is a ridge, a morainal ridge, and it's made up of white boulders. It's all blueberry land. The ice was here, the ocean was here. And this is a beach around here, a beach, because you got ocean, you're going to have beaches. Blueberry barrens up around Cherryfield, around the baseline, and these are 10, 20-foot high ridges, and the ice was probably doing this. Comes forward in the winter when there's less melt, melts back, comes forward, melts back, comes forward, comes back. Ice does not move backwards. It doesn't flow backwards, it melts backwards. So the best way to talk about it is that the ice always moves forward, but when the melt forces take over, the margin recedes, but the ice is still moving the same direction. So the ice is obviously melting back and leaving these 10-foot high ridges or so. Another example of a glacier I worked on the Yukon many years ago. This is a moraine of this glacier. The glacier had so much debris in it, as it melted down, the debris accumulated on the surface. So it doesn't look like ice, but it really is. The outer edge did this, came around here, over here, out here. This is interesting. This river flows into the Arctic Ocean. This flows into the Pacific, in that direction of all things. But I wanted to point out, this is a river, and this is 1730. This is the height of what we know as the Little Ice Age. And this is a bubbly thing here, water coming up 20, 30 feet. It's coming out of a tunnel back in the ice. The ice is melting here, it's going down into a tunnel, and exiting at this point and flowing out as a river. We had the same thing happening here. This is the edge of the Greenland ice sheet with a tunnel, just an example of a tunnel. That's all ice. This is ledge. That's ice, that's ledge. But there's a tunnel in the ice right there. And when the tunnel fills up with sand and gravel and the ice melts away, you have a ridge like this. This is called an esker. Maine's got the best eskers in the United States. There's an esker that feeds Cherryfield. If you trace the ridge back, you end up in Baxter Park. It's called the Katahdin Esker. It's 100 and some odd miles long. It's a river beneath the ice. And that's what this is. The ice melted away. This is the river bottom, just collapsed. Sand and gravel, biggest source of sand and gravel income in the state of Maine. Here's a cross-section one in Stratton, Maine. As it collapsed, this was the river bottom in the ice. The ridge runs into the picture. As it collapsed, it dropped down on this side, dropped down on this side. And if you could look at the layering in here, it'd be sort of horizontal in here and then just collapses on both sides when the ice disappeared. Another form, when those rivers under the ice exited the margin, the ice margin, and this is down in Dubois, and this is all big blueberry barren in here. The ice went along, I can't prove it to you, but it went along like this. This was a river channel, but it goes into an esker that goes way, 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 way over here. And as it came to the edge, the meltwater and all the gravel debouched into the Atlantic Ocean and formed this flat surface with slopes on all sides. That's a delta. And the blueberry barrens look like this underneath. This is a delta. The ice was on this side. The ice spit out sand and gravel in a river system. It went into the ocean, got to the edge, did this. Went out further, did this. Went out further, did this, until the river stops. And now we have these deltaic features. You can tell by the structures on them. This is the big blueberry barren at just north of Cherryfield. This is the road along here. And this is called East Base. Some of you know where this is. This is the east end of the surveying baseline that was put in 1853, and without getting into it, but there's a marker there. And this is the surface of the delta. That's this surface here, like this. And the edge of it is here. The ice stood here. And as the ice pulled back, the delta stopped forming. It's all sand and gravel. It stopped forming, and then the ocean, which it was building into, the waves simply went to work and cut this shoreline. This is an ocean shoreline, just like you see on Cape Cod today. It's exactly the same thing. It's 250 feet above sea level, however. And all around the hills of Acadia, we have beaches just like this. This is a terrific example. This is the best elevated shoreline, emerged shoreline we have in this part of the world. We've traced it from the New Hampshire border to St. John, New Brunswick now. It's everywhere. This sand and gravel in here, there's about 200 feet of it in many places. It's a very, very thick deposit. This is the cliff. We're right here, all right? We're going to look at that cliff right there. There's the cliff. Graduate students come in very handy. You just line them up. So this was the shoreline, the storm high tide. If you were going to put your beach blanket down on your lunch, you wouldn't put it there. You put it down here because the sea level would be along there, but in bad storm days, it would be up here beating against that cliff. It's duplicated anywhere on Cape Cod or many other places in the world. This is a beach. The whole thing is a beach. This is one of the little glacier, it's the biggest glacier that's called an outlet glacier for the Greenland ice sheet. It comes out through the mountains, and it's floating here. This is very much like it was along the Maine coast. It's floating back here. This is a floating shelf. But you notice the color. This is the Davis Strait. This is the ocean. And you notice the color of the water. That's rock flour. That's going to become clay, which we make bricks out of in Maine. And here we are with a general, I'll come back to that in a minute. Here's the general view of the receding margin, ice margin in Maine as it went back. We ended up with little pieces of ice up in here that lasted till about 10,000 years ago. But this was the shape. Notice all of a sudden there's a big embayment in the ice right here. This was the ice. And this is all flooded. The ocean followed this right in and covered all of this part of Maine, including where we're sitting. And that's what it looks like. This is the ocean, how far the ocean came in. These red lines are the Eskers. And you notice they form at right angles to the moraines. They're all over the state. And this was the ocean up to Millinocket here, and up to Bingham here, and up to, can't think of the name of the town over here on the Androscoggin. But that was the area underwater for Maine. And I've shown this to national audiences, and they don't know where I'm talking about until I point out that's LL Bean's. So now you know. We're right here, we're right there, yes? This is at Jonesport, right on the shore. And these boulders are washing out of till that's just below the surface. Above this is clay. This is the ocean bottom sediment, and it's absolutely full of ocean shells. When the sea drained away, this became dry land. There's a layer of sand, which is the beach, and then above this dry land, it became a peat bog, and then it became a house that eventually disappeared. As you can see why. They had to move the house. They didn't fall in it, they just moved it. But in one fell swoop, this is till the lowest part of the clay represents when the ice left here and the ocean started in, the ice went back, the ocean fell, and this is when the water fell off the landscape. So the time from here to here represents the time of marine submergence in the state, which is about 2,000 years. Good outcrop. That's all riprap now, you can't see it. These are the shells that live in that clay. This one's recognizable. These are recognizable, but they don't live here anymore. These are Pecten greenlandicus, and these are animals that don't live here anymore. But this one still does. And these are all found as a collection in the marine clay outside the front door here, down at the bottom of the hill. And they live today in the high Arctic, at least halfway up Greenland in the Arctic Ocean. So the ocean we were dealing with here was an Arctic ocean. And more to be said for that, but I won't get into it. But it was an Arctic ocean, and these are different species than the scallops that we have today. Here's an example now of land level change. This is in the Antarctic, and sea level change, but it's hard to decide which is which. For example, here's the shoreline today around McMurdo Sound. Nice clean beach, but up at this point, you see the beach turns into something darker color. So sea level was up here at some time and then abruptly dropped, formed beaches down, and so now we have shorelines here. So that's a land level, sea level change. And it's very clear in a place like this. Let's talk about this for a second. If you take ice and put it on the land, the land depresses. It's very analogous to pushing your finger into an inflated balloon. It goes down under the weight of the ice. How much ice? 3 feet of ice will make the crust of the earth go down 1 foot. Granite bodies, everything, 1 foot. 3 miles of ice, the crust goes down 1 mile. It's a 3-to-1 ratio. It's a floating equilibrium situation, just like a rowboat, because the subcrustal material is plastic on the earth. So if you put a couple of miles of ice, and we had 2 miles of ice right here at the maximum. 9/10 of that, we're down a long ways. But then you take away the ice, and the land bobs up. But at the same time, in taking away the ice, sea level is coming up. So sea level comes up, land level comes up, and finally it's stabilized the way it is today with shorelines up at 250 feet. But this is around Hudson Bay, and these are lines of uplift around that ice sheet. And here's a case of the land coming up and relative sea level dropping, beach after beach after beach after beach, all compressed. Maine is like that. The first beach is up around Millinocket, and the last one is at Bar Harbor. It's spread out. We have beaches all over the state like this. And you can find them easy enough if you put your mind to it. But here, they're compressed in a way. Let me look at the next picture for a second. Oh. That's where we were. I want to point out, I'm going to change the subject now a little bit. That's the history. Now let's look at what's going on. But I want to point out something to you very clearly here. This is a core from a temperature derived from an ice core in Greenland. And what it is 14 1,800 years ago, this has to do with snow accumulation. Snow accumulation was quite low. You get to this point and it changes, and snow accumulation is very high here. That accumulation, two accumulation rates is related to temperature change. The low accumulation is very low rate of snow. For example, in the Antarctic, the average snowfall is 1/4 of an inch a year. We get more this afternoon than they get in the whole Antarctic continent in a year by many factors. Well, all right, so what I want to show you is it's a climate change in here that goes from warm to cold, and the transition in here takes place in a matter of 10 years. A major transition. If we had this happen here, tomorrow we might have ice, snow that doesn't go away, and we're in another ice age. Yesterday it was warm. 10 years ago it was very warm. Now we're changing it around. So my point in all of this is to say that climate changes on many scales. One of them is very, very abrupt, and that is a danger that isn't very clear to a lot of people. We can also get a slow sinusoidal curve. But the last ice sheet started about 60,000 years ago, 60 million years ago. This is the end of the dinosaurs. Never mind all this. This is a temperature curve from 60 million years ago. It gets colder in this direction. So it's getting cooler. The Earth is cooling until we get to there, and then it gets into an oscillation type of cooling. And this is the beginning of the last ice age, and that's 2.5 million years ago. And we had ice to New York at that time. And because of the fluctuations, we had many events like this. But the Earth finally refrigerated to the point where we could do this. And this is related to continental drift, getting the oceans, the ocean circulation pattern changed around a bit, and it allows ice sheets to form. So that's where we are. Some of this, the pulsation in a glacier age, is related to the position of the Earth relative to the sun. And at times, we're a long ways, sometimes we're very close. And then sometimes we have this type of orbit. And the Earth also has got a tip to it, and so there's a tip to it, and there's also a wobble to it. So you got 3 dates, 3 positions, and each one of those determines the amount of radiation from the sun that hits the Earth. This was calculated for about a couple of million years by a man named Milankovitch in 1935. He calculated the amount of heat landing on square inches of the Earth for that period of time. His name was Milankovitch, and he did this without a computer. He did it with a piece of paper and a pencil. It's always good to tell students that they don't need an arithmetic calculator. But if you put all of those radiation curves together, they form cold, warm, cold, warm, cold, warm, cold, warm. And then over here, they relate to ice. The blue is ice. The ice expands in the Earth, falls back, expands, falls back, expands, falls back, expands, falls back, expands, falls back. And it's out here. This is 20,000 years ago now for us, and we're down in here. So the Ice Age is composed of a series of these things. Give you an example out of different ways to look at it. These are out of these are from ice cores on this side. Ice core is drilled. Each layer is analyzed for temperature. We have an ice age here that goes up here, and all of a sudden it gets warm. Here's the end of that, down at 15. Well, never mind, that's the depth on the core. And then it goes down into a warm period, another ice age starts. Same thing is true in the oxygen isotope ratios in the ocean, which give ocean temperatures, warm oceans, cold oceans, warm oceans, warm oceans. And then if you look at vegetation, you get the same thing. But the point is, all of these cold spells line right up whether you're using vegetation, water temperatures, or temperatures in an ice core. They're all the same. So we have a long record in various ways. This is what a glacier looks like when it accumulates, and you can see it's layered. Those are annual layers. If you put a core into that, you core through the annual layers, and each one is 1 year, 2 years, 3 years, 4 years, 5 years. University of Maine put down the deepest core ever put down on the Greenland ice sheet. It's 2 miles deep. That was done at Orono. No one knows about it, but all the people are still there. Here's what one looks like when you extract it from the drill core. That's what the ice looks like, and they put that in a laboratory, clean it up. You can calculate chemistry out of that, dust in the air, all sorts of parameters come out of that. And this is the way we know how the CO2, we now know that we know exactly what the CO2 level in the atmosphere has been for 500,000 years and more. This is how you know, because in a snowfall, air accumulates, and the air, as the snow compacts, the air gets isolated. So each one of these little air bubbles contains the atmosphere at the time. So you take those bubbles out, analyze them for the atmosphere, and you find out how much CO2 is in the atmosphere. That's how this is known. It's not guesswork, it's pure snowflakes to bubbles. Going back to Agassiz, again, a little bit. He said the climate changed, the animals changed. This is Los Angeles at the height of the last glaciation. And look at the animals, bison, mammoths, short-faced bears, all sorts of interesting animals on the landscape. We had them here too. We had mammoths in Maine. We have one mammoth remain, but you can't have one mammoth. People evolved during this time in the warm spells mostly. These are Neanderthals along the Mediterranean. I had my DNA calculated not too long ago. I'm 4% Neanderthal, as you are too, for the most part. We know what happened to the Neanderthals. They crossbred with Homo sapiens like us. And they didn't die off unilaterally. So people are the product of the Ice Age. And the earliest people in North America were Paleo-Indians. They're called Paleo-Indians. And we have very few remains in the Northeast here, but we have some. And they're characterized, they were hunters and gatherers, and they produced these beautiful projectile points. These aren't arrowheads, projectile points, and they're always characterized by a flake taken out right there. And that's the characteristic of the Paleo-Indian landscape. And they came across the Bering Land Bridge, and when the ice sheet melted back here, they came down this way, or they came down the shoreline. And the oldest sites are down here. Forget this for a minute. That's a very questionable age. The acceptable age for the peopling of this part of the world and down here is really 13,000 years now. And that's about it. The populating of the Americas took place at 13,000 years when this landscape opened up and allowed it to happen. And we have them in Maine. Now, I told you that the land level came up. Here in Maine, the land was depressed. The ocean was way back in here. The land level rose faster than the ocean. The ocean drained out, went all the way down here to about 200 feet below the present level. That was the shoreline for a while at 10,000 years ago. And ever since then, sea level has risen up to where it is today and is continuing to rise. So we had these are the shorelines of Maine. And you can see this happening, just to put it in perspective. This is outside of Helen's Restaurant in Machias. Across the river, there's docks that were built in the heyday of lumbering. Today, there's a working surface, a walking surface there. People walked on that surface. Today, at high tide, that surface is underwater. They didn't build the docks underwater. So there's an easy example of recognizable sea level change. We also see it today in the tide gauges in Portsmouth. This is the sea level rise to 1990. Here it is here. It's highest in Eastport. Why that is, we don't really know. And we're back to this again. And I just want to point out to you that within any one of these ice times, there's forward, backward, forward, backward, forward, backward, a lot of little variations. And as the ice receded the last time in the Alps, let's say after 20,000 years ago, we had renewed glaciation. In the year about 1,000 years ago, the little ice age set in, the global temperatures dropped 3/4 of a degree centigrade around the world, and we had glaciers expand like this. This was about 1750. There's a building. This is the Rhone Glacier in the Southern Alps. Today, it's up here. Same picture. Okay? It's all gone. Interestingly enough, on this road right there, there's the road. This is the road over here somewhere. You can see it. They built a couple of hotels up in here that you could walk from the hotel onto the ice, but now the hotel's there, but there's no ice. This is Lanso Meadow in northern Newfoundland. This is the only Viking site in North America that we know anything about. The first one ever found, and the Vikings were traveling around, probably along the Maine coast. A group of us have been working on that problem, but this is on the northern tip of Newfoundland, and those are the remains of the buildings. These are people from the Greenland colony coming south to collect wood and other things. And that's right on the shore in the northernmost part of Newfoundland. And there's a reconstruction of what those houses look like. It's a national park. And that's the way it is. We should have those in Maine, but we can't find them. But this was a Viking site. At the end of this time, the Greenland colony failed. It was successful for 500 years, longer than the United States has been successful, I might add. But they failed because the temperatures got very cold. The principal product, two principal products were butter, because they raised cattle in southeastern Greenland, and that stopped. They couldn't raise cattle anymore, and they sent walrus ivory to Europe. That product, walrus ivory, was called valuta, which means that's where the word value comes from, out of the Viking settlements of Greenland. And but that's the colony at Lanso Meadow. Now, another quick business to look at, if you can bear with me for a little bit. This is the great circulation of the ocean currents of the world. The bottom is subsurface bottom circulation, and this is surface circulation, and this is the Gulf Stream up in here. And the water goes from the equatorial region, carries heat northward, and carries the cold water southward. And that's what keeps the north warm. That's why we have palm trees in Cornwall. We have palm trees in west coast of Ireland, so forth, because it's very warm. And yet those countries are at the level of Greenland. Let me give you an example of what happens if you disrupt the Gulf Stream, the warm water going north. This is a phase in the recession of the big ice sheet. And you can see that right there, it's connected to there. This is the St. Lawrence Valley. It was blocked right there. When this pulled back a bit, all this water, connected water, flowed around here, out through here, into the North Atlantic, and the Gulf Stream was stopped dead by the flood of fresh water in the North Atlantic. I won't go into why that is. I'd be glad to tell you why. But the Gulf Stream stopped, and we immediately went into another ice age. Here's a case in point. This is past, this is getting warmer and warmer and warmer here, and we're getting warmer and warmer, all of a sudden, wham, we're in 1,000 years of renewed glaciation. The Gulf Stream stopped at that point. We went back into another ice age for 1,000 years, out of it, and back to the present. At the present time, the Gulf Stream is slowing down. Think about that. Getting in a tighter situation here in Maine, these are, give you an example of this, just an example. This is from a book that we did at Orono a number of years ago, and it shows the, from 1950 to 1720, and these are the dates of the last spring agricultural killing frost. And this is the summer, and this is the first killing frost in the fall. So in here, this represents the growing season. This is a Julian calendar. In other words, the 1st of January is there, the last day of the year is there. It just counts up. It's a good calendar compared to what we have today, but I think it's named after Julius Caesar, of course. But what I want to point out to you, there was virtually no growing season in here. These are the days, you count those things up. You couldn't hardly grow anything here. And one year would be this much from there to there, the next year is from here to here. Next year it's here, next year it's there. And this is back before we had many farms. But when you get up to 1880 and 90, right in here, there's a major change. You notice what happens? The noise goes bup, 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 and the growing season expands out to the point where you can grow normal crops. It takes 207 days to grow a potato. You couldn't grow a potato field back here if you had to. They wouldn't survive. But this is the beginning of North American agriculture. We came out of the little ice age in 1880. That was the end of the little ice age. And here's what happened. So this is the beginning of the present, and this is what caused the great expansion of American agriculture, along with know-how, but without this, it wouldn't make any difference. So there's a lot of stuff like this around that we actually live in. The year 1816 is the year without a summer. I don't have a good record, but the growing season in 1816 was 0 in Maine. We had killing frosts every month of the year. Nothing grew in Maine. And there's an example of it. I'll read it to you. In 1771, Reuben Whitten died in 1847, son of a revolutionary soldier, a pioneer in this town. During the cold season of 1816, he raised 40 bushels of wheat on this land, which kept his family and neighbors from starvation. That's 1816. That's when the great migration from Maine left, and they went to the Ohio River Valley very often via a street called Ohio Street in Bangor. That's where the eastern farmers flooded out towards the Ohio Valley, and hence the name. So we do have these things. One more little diagram, and I got it backwards, I'm sorry, but let me point out what it is. Not a very good picture. But the Ice Age is a series of times of ice where we have 100,000 years of glaciation, and then a time like this, called an interglacial time. It lasts about 10 or 15,000 years, and we go into another 100,000 years of ice, another 15, 20,000 years. This has to do with the climate positioning of the planet. And here we are. This is backwards. Here we are today. We've come out of the ice at 20,000. We got warmer and warmer until 4,000 years ago. And then we've been getting colder ever since until we got to about the 1880s, and the CO2 level started to go sky high. So we were well on our way into the next glacial period before the Industrial Revolution started, or we started in on the global climate change we have today. And here we are. You can see what's happened here. This is a graph of carbon dioxide and temperature. Here's the temperature, CO2. This is temperature. And you notice the CO2 goes up, temperature goes up, CO2 falls, temperature falls. Temperature is up here now. It started right there to go the other way and reversed itself and came up to here, but we're behind times. The temperature should be much higher because the current level of carbon dioxide is up there. The temperature is trying to catch up to that. We're at right now, this is a couple of years old, we're at 400 parts per million now, and the temperature hasn't caught up to it yet, but it's going to, and the prediction is 800 to 1,000 parts per million, which is affecting the Earth at the present time, unless we do something very quickly about it. And I just point out that we grow very large blueberries in Maine. And there's the Ice Age Trail. This was a concept map originally, but you can see what it is. It covers this. It's a bunch of individual driving stops that take you through all of the things we discussed right down to Lubeck, starting at the top of Cadillac Mountain. And this is the way it did it. The ice moved back, moraines were formed, deltas were formed, Route 1 picks up here, goes up here, over the deltas, down onto the moraine. That's the sort of scenery that you see. I'm sorry I got these backwards because I didn't have a chance to review them. Something happened in here I won't go into. Now, just to point out that all things don't act on a slow scale. We have volcanic eruptions we have no control over, like Mount St. Helens, which is a tiny one, like Tambora that set off the little ice age, 1816, devastated agriculture around the world. And here's another kind of thing. This is the tidal wave tsunami at Aceh in Indonesia that happened about, what, 10 years ago? It happened because there was an offshore fault, the wave. Just think about this. Those are cars, and that's coming right at them. That's a 100-foot wave that's going to kill everybody in that picture. This is taken from the top of a high-rise building accidentally by a remote camera. We have these in Maine. The last one was it was about a 2-foot wave that came into the mid-coast region from an offshore fault. But look at that. That's the kind of thing that can happen anytime, anywhere, and we don't know when it's going to come, and it's unpredictable. Now, the University of Maine has been very good to me and a lot of other people, and they just recently completed this building for us. This is the Climate Change Institute on campus at Orono. My office is right there. But before you come in the building, when you come here and look for this, you've got to take your shoes off right there, and then you can come in the building. And that's all I have to tell you. How's that? Sorry to keep you so long. Yeah, I was going to show you one other thing while I got you here. Hang on to this for a minute. I just want to show you something. This is what an ice age looks like. The pictures were inverse, but we have these warm spells, warm spells, ice age, cold, ice, cold, and it's a sawtooth arrangement. And we're coming out of the ice. That's 4,000 years ago here in Maine, and we started to get colder, and all of a sudden we're going this way again, up into warmer and warmer climate. If you turn it over and look at the CO2 levels, I'll just leave you with this. These are CO2 levels measured in temperature things that we did, and back in time to 800,000 years, and we get CO2 levels, and the temperature goes with the CO2. So it gets colder and warmer and colder and colder and warmer. And we're within the bounds here, and it never gets, for the past 800,000 years, the CO2 level in the air has never get above 280 parts per million. It's not very much. But today, it's risen to 400. And we're headed very quickly to that level. And I'd like to point out to you that this whole picture here is what constrains global climate models. The boundary, these are the boundaries of the ability to do this. So what I'm pointing out to you, once the CO2 gets above this, we're in a state of free fall. We have no way to predict what's going to happen and how it's going to come down and stabilize. It might stabilize in another ice age. That's the prediction. But we're way, way out. The last thing I'll leave you with, a recently published report from Harvard last spring reported out a long-term study, the second one of this type, where they put people, a statistical population in a room, and they raised the level, they asked them questions of decision-making. You put a picture up, you turn left or right, you go up or down. And then they raised the CO2 levels to 1,000 parts per million, asked the same questions. And what happened? The human cognition failed. They couldn't answer the questions right. So as the CO2 goes up, we get dumber and dumber and dumber. And as someone pointed out, CO2 levels are very high. And this hasn't made the public, I don't know why it hasn't. This is the direct effect on you and me. And in big buildings like schools, it's well above the level of 400. And in the halls of the United States Congress, it's way up, and that accounts for some of it. But seriously, this is affecting humans, and it isn't going to change. It's dumbing us down physically. It's a very good report. Well, that's all I got to tell you about that.
Thank you. So we can take a few questions, but so that Dr. Borns can hear your question, we'd love for you to use this mic, and this mic works best if you put it near your mouth. If you put it near your mouth, it works. Okay? Raise your hand if you have a question.
This isn't working too well. I'm going to get
the Laurentide ice sheet, which came down and covered us. How thick was that? I know I've heard that it was a mile or two here at the edge. How thick was it in Hudson Bay or wherever the center
probably
of it
about
was?
2.5 miles thick. The ice sheet gets very steep quickly and goes like this and flattens out. So the slope way back is maybe less than 2 degrees on the surface, but it's parabolic. And so it's very steep in the beginning and then flattens out. So about 2.5 miles, probably. 2 miles here.
Okay.
One lot of ice. And there's a very simple way to calculate that. If you ever want to calculate it for students, I'll show you if you want to know. Okay. You want to know? I need a pen to write on here. Maybe there's one here. The whole purpose of the United States, or periodically the world gets together and calls a year the geophysical year, and all the physical scientists of the world get together and make uniform measurements all over the earth. They measure whatever they measure gravity or whatever. Well, in 1958 through 61 was the so-called last geophysical year, and the role of the Antarctic, they wanted to know all about the ice sheet, because just prior to that, when I was a graduate student for a while, for example, they didn't know how thick that ice sheet was. Some people were saying 1,000 feet, some 500. It's 3 miles thick. And so they set out to measure that. And no. Oh.
Someone is looking.
Oh, okay.
I think a regular pen won't help that much.
So what they did, the U.S. and other countries put together tractor trains, and they drove from the edge of the ice sheet up on it, and then they get to a certain position and they blast off. That's all. Yeah, they start here and go up to this point and blast off some dynamite and retrieve it on a seismometer, and they can tell how thick that is. That was referred to as H. And then the distance from the margin to here was called X. So they go a little bit further and do the same thing. And X is now this, and so it goes. So now they have the distance this way and the thickness that way, and they put together an empirical formula to fit that situation. It fits, it's made to fit that. And the formula is the height, thickness equals 4.7 times the square root of X in meters, like that. Very simple. So if this is Bar Harbor and this is Mount Katahdin, you can measure that distance and then using this calculate that distance, and you find Mount Katahdin, when the coast was uncovered, Mount Katahdin was still 2,000 feet below the surface of the ice. So it's an empirical formula. There's another formula that's very different, and it's calculated a different way mathematically, but this is the empirical way of doing it, and you can use it anytime. It's very simple, but you got to make sure you put everything in meters, not kilometers, but meters. So convert miles to meters.
Hi. In that previous chart, what caused the carbon to rise and fall to cause the temperatures to rise and fall?
Well, partly it's solar radiation. Question is, where does the CO2 rise and fall? For example, let me give you an example, an analogy. If you take a bottle of Coca-Cola, open the top up, take it out, take the cap off, put it in the refrigerator, the next day you've got just as much CO2 in the bottle as you had when you took the cap off. If you take the bottle out and warm it up, the CO2 disappears. So a cold ocean sucks in CO2, a warm ocean puts it out. So that's part of this cyclicity. So you go from warm to cold seasonally, and then you add in the factors that Milankovitch came up with, and you get some figures, and that's one way. The other way is do what we do, and we're burning fossil fuels, basically. And that's what's doing it now. But the temperature exactly follows the CO2, and nitrous oxide and all these other greenhouse gases. More CO2, the higher the temperature. Some people don't believe it. But you know, a good example of science deniers, and we have a president that's saying just that. You ask someday, you go to a medical doctor at all? Yeah. You take pills? You take internal medicine? Yeah. How do you suppose that internal medicine was made? That's science. Why do you believe it in medicine? You don't believe it anywhere else? Might think about that. The other approach is, well, that's what you think. We'll just go about our business. Anyway, we live in a really, really interesting time. I mean, it's not a good time in many ways, but it's certainly interesting to see what we're going to do. President Trump has already set an order in motion removing all climate change research money out of all the federal agencies like NOAA, every bit of it, except for the National Science Foundation. There's too much pressure there, but we're losing it. George W. Bush did the same thing, exactly the same thing. We all came back again. All right. It's frustrating, yeah. Yeah.
As they remove that funding, what kind of impacts does it have for the continuity of data gathering?
Say it again, I'm sorry, I've got a hearing aid problem.
That's fine.
Yeah.
As they have removed that funding for climate study, what kind of data or what kind of impacts does it have for data gathering?
Well, unfortunately, that kind of funding we have now satellites that sense, they're Earth sensing satellites. So they fly around and they measure the temperature of the atmosphere everywhere. They measure sea level change and temperatures everywhere. They've been measuring the loss of sea ice in the Arctic. That's all going to disappear. All those sensing systems. Well, I don't think they're going to. I mean, I think common sense is going to set in. We're going to have to do something about it. But one of the areas that's of concern that is always research to be done. And one of the areas of research that's been going on for quite a while now, without a good answer yet, is what causes abrupt climate changes. Abrupt. I mean, you go along like this, and then 10 years later, we're living in conditions that exist today in the Arctic, and we're still living on the coast of Maine. That type of abrupt change, and it's real. I mean, we have that kind of change recorded in many places. And how do you predict that kind of thing? And right now, using this type of thing, as I pointed out, the models, mathematical models that control and allow the prediction of this into the future are no longer operable because we're out of that's a boundary condition, and that's a boundary condition, and the model works here, and we can predict it, and if we predicted it right there, we're just going into the next ice age. That's where we were well underway into the next ice age, because we reached the bottom here, bottom there, we reached the bottom here 4,000 years ago, and we're going into the cold, and so it goes. This is the bottom. That's the warm part when we had cypress trees growing in Boston, and all sorts of swordfish in the Gulf of Maine, and the great mass migration of Indians to the coast to take care, the whole Gulf of Maine changed. That was 4,000 years ago. It's been getting colder ever since until about 1900, and wham, it reversed, and that's the rise of CO2 due to burning of fossil fuels. It's there, but we're outside the model. We don't have a model for the future, and that's one of the problems. What do we do in the future? And as a matter of fact, if you think about this, the slowing of the Gulf Stream, and we have buoys floating in the Gulf Stream, and they're tracked by satellites. The Gulf Stream seems to be slowing down. That means it's transporting less heat northward, and it's slowing down because we're flooding the North Atlantic with fresh meltwater from the glaciers. And that fresh water is like a cap, prevents the salt water from evaporating and making the surface of the salt water heavier with a little bit of heaviness due to the concentration of salt. And then in the Arctic, that gets so concentrated, it sinks and goes on North Atlantic bottom water back to the equator and down. So that's what drives the Gulf Stream. If we flood the surface with water, fresh water, prevents the evaporation of the salt water, the Gulf Stream stops dead. And we're instantly in an ice age. So one of the predictions right now, based on that kind of thing, is the present global warming is the trigger for the next ice age. Think about that. There's a movie made of this. It's called The Day After Tomorrow. Did you see that? About 5 years ago. That's exactly what happened. They took that scenario and compressed it in time, and we all of a sudden we're in an ice age, and snow was accumulating in snowbanks all the way down to New York, and the president was frantic. They don't know what do we do. We moved south. We can't move the people from the north. They're in little isolated areas like Portland, Maine. They can't get south anymore. And so we just got to worry about citizens that live south of New York, and we're going to move them south. Then the question was, will the Mexicans let us over the wall? And the answer was no. The Mexicans had nothing doing. It was a great movie. Yeah, I recommend you get it.
I think we'll do just one more question as a group, and conversation can continue after that.
I guess the question I have after listening to this is, how accurate is the data that we have about CO2 levels in the atmosphere. We're looking now, of course, in modern times, we have more accurate record keeping. As you move backwards, is it possible to differentiate, the word escapes me, with any accuracy? We're looking at 100 years right now, 100 years of rapidly rising CO2.
Yeah.
Is it possible that our data is not accurate enough to pick out 5, 20,000, 100,000 years ago, 100 years of rapidly rising CO2? I mean, you told us
Yes.
that without the rapid rise in CO2, we would naturally have been heading into an ice age right now, according to the model. And you're saying that because of the rapidly rising CO2, it seems likely or theoretically possible that that may be the trigger that puts us in another ice age. So I guess my question is, how do we know that that's not always been the trigger? How do we know that throughout history, the trigger for ice ages hasn't always been a rapidly rising...
I see what you mean. First of all, this figure of 800,000 is short. The real figure is out here to several millions of years, where we really know what that is, the CO2 levels are. And it looks just like this. There's no real change. The last ice age we had prior to this one was 200 million years ago. And it occurred on all the continents of the southern hemisphere. Since then, those continents have broken up. Some of the record is, the footprint is in India, Antarctica, Australia, South America. And that's been one of my long-term research. I've been working on this stuff in those countries for many years. And the record is there, and then the one before that was 600 million years ago. It's pretty clear, but the record is pretty obscure by that time. So they're not something that appears periodically like clockwork. It has to do with the way the continents come together. For example, the Isthmus of Panama has been closed for about 25,000 years. Before that, it was wide open. So the ocean, there was no Isthmus of Panama. The water went from the Atlantic to the Pacific, back and forth. So the circulation of ocean waters went through from the Pacific to the Atlantic and around the world at that time. And as continents collide, for example, like India comes from being attached to the Antarctic, it's drifted north and run into Asia. And whereas it hit Asia, it's driving underneath Asia, and the Himalayas are coming up as we speak. They're still going up. And so that situation, or the building of the Alps, which didn't exist prior to the last ice age, have come up for the same reason. And that throws the atmospheric circulation a bit amok. And so that circulation belt that we have today moves warm water north and cold water south, only exists today during the present. And in the days of the Isthmus of Panama closed, it was a very different world. But if you do it just right, and you can stop that great ocean heat circulation and the atmospheric circulation, you can cool the north and the south and make the central part warmer. And that produces an ice age. So the big picture is driven by continental drift with the solar radiation variation superimposed on it to give you the little wiggles in it. That's what, prior to, first paper I ever wrote on the geology of Maine was from the quarry down at Limestone, in Thomaston. They found in a crevice, a big deep crevice in the limestone where the quarry is, they found some soil. The soil had been truncated by ice moving over it. Here's this big wedge of stuff down here. We analyzed it, and that's the soil that existed prior to the last ice age. And it's exactly the same conditions as Georgia today. So prior to the beginning of the last ice age, this state resembled Georgia in terms of heat and humidity. Very, very different. But then we changed. But that's not continental drift in this case. This is climate change. But anyways, does that get you there? The way the bubbles are treated, the assumption is, and I think it's a good assumption because it's been brought right up to today, pretty much. The bubbles are taken out and the percentage of CO2 is measured directly. The assumption is that little bubble contains the atmosphere of the time completely. And so that's where the CO2 levels come. And today, you can measure CO2 day in and day out, but you get local variations. But the satellite business helps to do that. They're measuring it all the time at the top of the atmosphere. It is. So it's getting a better homogenized global picture of CO2 rise. And they've been measuring this on the top of Mauna Loa for 50 years now. It's an observatory there in the Hawaiian Islands. It's the first, only observatory for a long time. And they have day in and day out records for about 50 years of CO2. Just direct measurements. Yeah.
So when you core sample and you're able to measure those air bubbles, how far back in your core samples are you going? Maybe that's getting at the gentleman's question. How far back in those core samples can you actually measure?
Well, what happens as the ice thickens, let's see if I can show you. You can get back quite a ways. Gotten back about several 100,000 years easily in Greenland. And if you look at an ice sheet, what happens is accumulation snow comes in there and it goes like this, and it floods out. It's synonymous with taking a bucket of pancake batter, pouring it in the middle of the table. Just runs out in all directions. The place where it doesn't run is right there. So if you get and by ice moving like that, it smears, and you start to lose the layering. If you take the core here or just a little bit off there, you get really good records, and that's the way people calculate where is the best place to do the coring like this. To get away from the smears. But some glaciers you can't do it, they're just too small. One of the big rushes that's going on right now in the ice coring world, and it's an international effort, they're trying to figure out where are the best places to take glacier cores to get the best record before they all disappear completely. And so there's a prioritization, just like the archaeologists and looking at the shell middens along the coast. Which ones are going to give us the best record in the sense of raising sea level and destroying them? We've got to get that one and that one and that one. The rest of them we just let go. And that's what they're doing with the ice core world right now. Same way, trying to pick up ice cores that are on boundary conditions of climate. Different changes in airflow, we'll say, from the Antarctic up to Chile in the Andes. There's a separation there of ice, and there's all sorts of things like that that are going on. It's a big business. I wish I was 20 years younger. Had better hips.
Please join me in thanking Dr. Borens again.
I'll say one more thing. As I said, we have a very large ice coring group. We have a group, not just ice coring, climate change. And we're composed, at Orono, we're composed of glacial geologists, paleoecologists that deal with pollen, lake core people, lake analysis people, ice core people, chemists. This amounts to about 25 people now. We're the biggest group like this in the world at the present time, at Orono. No one knows it. Half of Orono doesn't know it. And we have an indoor core storage library And the cores that are collected that are usually less than 200 or 300 feet in length go into our laboratory in the cold room. So if you walk in, it's 30 below zero. And a lot of the work is done in there, 30 below centigrade. And then there are all sorts of ways to analyze it. For example, the core is analyzed for dust, volcanic dust. You can equate to volcanoes. Sea salts, when the ocean is changing circulation pattern and the ocean is flowing over Greenland, you get sodium chloride in the snow. You know, there's all sorts of chemistry things that you can do related to this. And if you're interested in this, contact us. We have one person who will set it up and take you on a tour of all this, how this is all done. Just in the ice core business. And you want to talk to an archaeologist, that's another case. But the ice core facility is a really good one. And you'd be surprised what can be done in ice cores. But contact me, and I'll set it up for you somehow.